Assalamualaikum warahmatullahi wabarakatuh. My name is Dayana Faridina binti Abdul Hakim. My matrix number is B0821104888 and I will be explaining some parts of the assignment. This was the question given to us and this was the block diagram of the question. To plot the root locus, this was the calculation that was done. We got 4 poles, no zeros. The asymptote angles are 45 degree, 135 degree, 225 degree and 315 degree. The asymptote crossing point is negative 1.25 and the J omega crossing is 1.414 with K 2.4. This is the calculation for breakaway and we know that the poles are located on negative 2 and negative 1. So the breakaway point will be negative 1.61 and the angle of departure is negative 45. And this is the root locus that was drawn from the calculation that we did. The dominant pole for damping ratio 0.42 was negative 0.5 plus minus 0.95. This is gotten from the graph where we got the angle 95.17. The settling time is 8.89 seconds and the peak time is 3.31 seconds and the overshoot percentage is 23%. This is all gotten from the value of dominant pole and we insert it to the formulas for each of the settling time, peak time and overshoot percentage. Meanwhile, the steady state area is 0.44. This is the system's performance on MATLAB. There is not much of a difference between the calculated and simulation. The difference could be because in MATLAB, it is a higher order system, so it is much more accurate.
As for suggestion to improve, the appropriate controller chosen was PID controller, so the new settling time is half the old one with 20% overshoot. The old dominant pole is negative 0.45 plus minus J 0.95 with gain 2.4 and the angle for damping ratio is 65.17 degrees. This is the formula to find new settling time, new sigma omega n and the new omega d. And this is the new value of all of them. Now the new compensated dominant pole is negative 0.89 plus minus J 1.92. After that, we have to find the angle of each of the pole using this formula, so the angle are both 86.72 degree and 59.97 degree respectively. After that, we will find the ZC to know the zero pole is located where, in this case, it is located at negative 3.81. Next, for the PD controller, we will get the GS to be S plus 3.81 and implement it to GPS as GS, which we will get the value of gain K using the dominant pole negative 0.89 plus minus J 1.92. The value of K is 1.54. For the PI controller, the value of GPI S is S plus 0.01 per S. 0.01 was chosen so that there is no difference to the dominant pole because the value is very small, so to find the new K, we will use the same dominant pole as before and we will get K value to be 1.54. The PID controller is when we implement all the PD and PI controller into one and get this new G as value. That transfer function is then compared to the formula for GPIDS to get the value of K1 and K2. This is the simulation for the root locus after improvement in MATLAB.
This is the plot that we got, and to find the value of GS, we will first change the denominator first, and then we will find the gain, and this is the value of the break frequency. Now this is the plot from the simulation. To improve the system performance, the lag compensator is added. This is the calculation for the lag compensator. First, after finding the value of gain, which is 1.58, that would give a damping ratio of 0.405. We must find the new transfer function, which is after that we will need to find new gain to improve the 10-fold steady state error and get a damping ratio of 0.405 by using the K be familiar, and then since the system need to improve tenfold, then the KP will be factorized by 10, and then we will find the new KP value. The new KP value will then be implemented in the GS. After that, we will have to draw the asymptote bird plot for uncompensated system and find new phase margin. We will also need to draw the high frequency 1 over period asymptote at negative 2 dB at frequency 0.98 radian per second. This is the value of for 1 per alpha, which is 1.26, and then we get the value of 1 per alpha times period. All those values will be then implemented into the lag compensated transfer function, and all we need is draw the compensated bird plot by combining the new GS and the lag compensated. This is the simulation bird plot for uncompensated, and this is the simulation for the compensated bird plot with the lag compensator.